So our next speaker is going to be Noushin Nasiri from the School of Engineering in the Faculty of Science Engineering. She completed a PhD in 2007 from ANU and is now currently a lecturer in the School of Engineering. And in 2009, she had a Young Poppy Science Communication Award, and her research focuses on the fabrication of nanoelectronic sensors for health and medical applications. Her presentation title is Breathe on Me.
Thank you.
Thank you.
Cancer. Everybody is talking about cancer these days. It's one of the leading causes of death in the world. In Australia, it kills more than 45,000 each year, and globally, more than 8 million deaths. But let me tell you something. Cancer itself is not a killer. It's late detection that takes lives. For example, lung cancer is usually detected very late, when the chance of recovery is less than 4%. But if we detect it at a very early stage, we might have 85% chance of recovery. So don't be afraid of cancer. Be afraid of its late detection. But early detection of disease is very tricky. Once it's detectable in blood, it means that it's already spread everywhere in the body. So we need to detect it before it goes into your blood. How? In my research, I'm doing this by looking at your breath. It might seem invisible, but your breath tells a story. And while that story can be used in RBT and put you in trouble, I can use it to save your life. You know, we smell different when we are sick. Our body chemistry changes when we are sick. And as a result of that chemistry change, some biomarkers are emitted into our blood system and then into our breath, and give us this unique opportunity of detecting disease just by sniffing out the breath. But there is one big challenge here. These biomarkers, they exist at a very low concentration, down to parts per billion. Here is an example. Acetone is a well-known biomarker for diabetes. Now, if 1 in a million parts of your breath is acetone, you're healthy. If 2 in a million parts in your breath is acetone, you have diabetes. So the biomarker's concentration difference between healthy people and patients is 1 part per million. How small is that? Let me visualize it. The entire Harry Potter series, 7 books, has 1,084,170 words, which makes the word Dumbledore on page 17 of Harry Potter and the Philosopher's Stone a bit less than 1 ppm. So in order to monitor diabetes using your breath rather than blood, we need super sensitive sensors capable of detecting ppm, or even less, ppb. Before nanotechnology, it was impossible to precisely detect such a tiny concentration. But today, we can make sensors hundreds of times more accurate than what we need. But how nanotechnology can help us to fabricate such a sophisticated sensor? It's all related to the available surface area. Here, we have a cube with the length, width, and height of 20 centimeters. Now, what happens to the cube surface area if I divide it into 8 cubes? You see, I'm not changing the material, neither its mass nor volume. I'm just creating more surfaces. So the available surface area is doubled. Now imagine if I keep dividing each of these cubes into smaller and smaller cubes until having cubes with 20 nanometer lengths. If I do that, we're going to have 10 million times larger surface area. Same material, same mass, same volume, but 10 million times larger surface area. In fact, by shrinking the structural elements of my sensors down to nanoscale, I can significantly increase the available surface area to capture that tiny concentration of biomarker in your breath. Nanoscience is not just one science, it's a platform that includes biology, chemistry, electronic, physics, material science, and engineering. It's shown its potential to positively impact our quality of life, and breath analysis as one of many research areas in this field. can empower us with more knowledge about our health, our body, and can help us to save many, many lives in the near future. Thank you.
How can you see so this relies on a biomarker, being able to detect biomarkers. How could you see joining this technology with the detection of other biomarkers all in one big?
So I can see that it has a big potential to do so. In order to do something like this, to kind of expand it to the other biomarkers, we definitely need an array of sensors, so it won't be possible with one sensor. Even for detecting, for example, acetone, it's important to have one sensor that can detect acetone, but it's also important, at the same time, you should have an extra set of sensors to make sure that you are detecting acetone, but not something else. But because the sensors are super, super small, so they are actually, they can be fit at the tip of a needle, we don't have any problem in terms of having, 100 sensors in one small chip together. But the research has a potential to be used for many, many other applications, as well as the medical application. Based on my knowledge, at the moment, we know the biomarker for 28 diseases. I'm working on diabetes as one of the diseases, but it can be expanded to many other diseases.
Any other questions? Okay, so we'll go to some of the questions from Zoom. Philippa asks, what is your view on the controversy surrounding the impact of overdiagnosis, e.g. breast cancer?
So the thing is that my understanding from this research is that it's not going to be a gold standard testing or diagnostic device. It's going to be, so in the medicine, it's like climbing up a ladder. So normally we start with a test which is the least invasive and is the least expensive. So I would see breast analysis would be as the first test that we can do. And if the test results is positive, then we can immediately go to the doctor and do the other, we can climb up a ladder and do more tests to make sure that the results are correct. But I look at this research as something that can be a portable and easy test and non-invasive test that everyone can do at home in order to make sure that our body is working very well. If there is anything wrong about that, then we can go to the doctor and we can, follow it up.
Thank you. So another question here from Jane. Is this process cost effective? Do you envision a rollout of such nanotechnology into GP offices? Are there any ethical issues to consider?
There are always some ethical issues to consider, but I'm very positive about this research. I'm not looking at it as something that has kind of negative impact on our GPs, So this is something that can help the society to be aware of any change in our metabolics, any change in the chemistry of our body. So then we can have a very frequent, a very easy way of frequently checking our body. But then, as I said, yeah, of course they should, because we're dealing with human body and we're dealing with human sample, which is a breast. We are always having some ethical concern which need to be addressed. Yeah.
And I guess one last question from me, demonstrating the nerd I am. You were increasing the surface area so much there. Does that mean you want to try and make the device fractal? Because in principle, that has infinite sort of surface areas.
So the thing is that of course, it's going to be some change in the structure of the device. But if you're talking about a device which is super small as a tip of a needle, that's not going to be an issue, I would say.
Okay. All right. Thank you very much.